Welcome to Sleepy Parallax. Tonight, we're going to explore the most profound mystery in all of cosmology. Imagine that everything you've ever seen, touched or known, every star that twinkles in the night sky, every planet, every atom in your body, represents less than 5% of the universe. The rest, the overwhelming majority of everything that exists, is invisible, untouchable, and yet it shapes every galaxy, drives the expansion of space itself, and holds the key to our cosmic future. Let's begin our journey into the darkness that illuminates everything. There's something deeply humbling about discovering that most of the universe is hidden from us. Not hidden in the sense that it's far away or too small to see, but hidden because it doesn't interact with light at all. It passes through ordinary matter, like a ghost through a wall, leaving only the faintest gravitational whispers of its presence. This invisible universe wasn't discovered all at once. It revealed itself slowly, reluctantly, through a series of observations that didn't quite add up. Measurements that suggested something vast and strange was at work behind the cosmic curtain. Scientists didn't set out to find dark matter and dark energy. They stumbled upon them while trying to understand other things entirely, and each discovery made the universe stranger and more wonderful than we had imagined. Picture yourself standing on a hillside on a clear, dark night. Above you, the Milky Way stretches across the sky, a river of light containing hundreds of billions of stars. It feels complete, whole, everything you could ever need to understand the cosmos spread out before you in points of light. But what if someone told you that all those stars, all that light, all that magnificent structure is just the foam on an invisible ocean? That for every star you see, there's 5 times as much matter you can't see, and even more mysterious energy pushing everything apart. The story begins, as many good mysteries do, with things not behaving as they should. In the early 20th century, astronomers were getting better at measuring the universe. They could determine how fast stars were moving, how galaxies rotated, how clusters of galaxies held together. They had Newton's laws of gravity, refined and tested over centuries. They had Einstein's general relativity, a more complete picture of how mass and energy curve space-time. Everything should have made sense, but it didn't. The first hints came from studying galaxy clusters, vast congregations of hundreds or thousands of galaxies bound together by gravity. These clusters are the largest stable structures in the universe, cosmic cities where galaxies swarm like bees around an invisible hive. When astronomers measured how fast these galaxies were moving within their clusters, they found something troubling. The galaxies were moving too fast, much too fast. Think of it like watching planets orbit the sun. The closer a planet is to the sun, the faster it needs to move to maintain its orbit against the sun's gravitational pull. The farther away it is, the slower it can move. This relationship between distance and orbital speed is precise, predictable, written in the language of gravity. If you know the mass of the sun and the distance of a planet, you can calculate exactly how fast that planet should be moving. The same principle applies to galaxies in clusters. If you can see all the galaxies in a cluster, count up all their stars, measure all the glowing gas between them, you should be able to calculate the total mass and predict how fast everything should be moving. But when astronomers did this calculation, the numbers didn't match. Galaxies were whizzing around their clusters at speeds that should have flung them out into intergalactic space long ago. It was as if you were watching a merry-go-round spinning so fast that the horses should fly off. But somehow they stayed attached, held by invisible chains you couldn't see. The only explanation was that there had to be more mass in these clusters, much more mass than anyone could see. Something invisible was providing extra gravity, extra pull, keeping these cosmic cities from flying apart. At first, astronomers looked for ordinary explanations. Maybe there were lots of dim stars they couldn't see. Maybe there were vast clouds of cold gas that didn't glow. Maybe there were planets, asteroids, black holes, all sorts of normal matter hiding in the darkness. They called this hypothetical hidden stuff missing mass or dark matter, dark only in the sense that it didn't shine. But as observations improved and telescopes grew more powerful, it became clear that no amount of hidden ordinary matter could account for what they were seeing. The missing mass wasn't just significant, it was dominant. There was 5 or 6 times more invisible matter than visible matter. The universe we could see was just the tip of a mostly invisible iceberg. This revelation changed everything. It meant that the cosmos wasn't primarily made of the stuff we're made of. Atoms, the building blocks of everything we know, were a minority component in a universe dominated by something else entirely. It was like discovering that what you thought was the ocean was actually just the surface tension on a much deeper, darker sea. The evidence kept mounting from different directions. When astronomers studied how light from distant galaxies bent around massive objects, a phenomenon called gravitational lensing that Einstein had predicted, they could map where mass was located. And again, they found far more mass than they could see. Invisible halos of dark matter surrounded every galaxy, extending far beyond the visible stars like vast transparent cocoons. Computer simulations of the early universe showed that without dark matter, galaxies couldn't have formed the way they did. Ordinary matter alone would have taken too long to clump together. The universe would look completely different, perhaps without galaxies at all, certainly without the complex structures we see today. Dark matter, whatever it was, wasn't just an addition to the cosmic recipe. It was an essential ingredient. But understanding that dark matter existed was very different from understanding what it was. This invisible substance didn't emit light, didn't absorb light, didn't reflect light. It passed through ordinary matter without stopping, like neutrinos but with significant mass. It clumped together through gravity, but didn't seem to interact through any of the other fundamental forces. It was everywhere and nowhere, shaping the universe while remaining stubbornly hidden. Scientists began to realize they were dealing with something fundamentally different from ordinary matter. This wasn't just stuff that happened to be dark. It was a different category of existence altogether. It might be made of particles never seen in any laboratory, particles that barely interact with our world except through gravity. It might be primordial, left over from the first moments after the Big Bang. It might obey rules we haven't discovered yet. The search for dark matter became one of the great quests of modern physics. Deep underground, in abandoned mines and beneath mountains, scientists built incredibly sensitive detectors, hoping to catch the rare moment when a dark matter particle might bump into an ordinary atom. In space, satellites looked for the telltale signs of dark matter particles annihilating each other. At the Large Hadron Collider, physicists smashed particles together at tremendous energies, hoping to create dark matter in the laboratory. Yet despite decades of searching, dark matter remained elusive. Every experiment that failed to find it narrowed down what it could be, but also deepened the mystery. It was like trying to catch smoke with your hands, knowing it's there from the shadows it casts, but never quite grasping it. And just when scientists were getting comfortable with the idea that most of the universe's matter was invisible, another discovery made everything even stranger. Not only was most of the matter in the universe dark, but there was also a mysterious force pushing everything apart, a kind of anti-gravity that nobody had expected. This dark energy, as it came to be called, made dark matter look almost ordinary by comparison. The universe, it turned out, wasn't just hiding most of its matter, it was hiding most of its energy too. And this energy was doing something that seemed impossible. It was causing the expansion of the universe to accelerate. Space itself was stretching faster and faster, driven by an invisible force that filled every cubic centimetre of vacuum. Together, dark matter and dark energy composed 95% of the universe. Everything we could see, everything we were made of, everything we had studied for centuries was just 5% of reality. We were living in a cosmic democracy where ordinary matter didn't even have a significant vote. This discovery was both humbling and exciting. Humbling because it showed how little we really knew about the universe. Exciting because it meant there were vast new territories to explore, fundamental discoveries still to be made. The universe wasn't nearly finished surprising us. As we drift deeper into this mystery, remember that darkness isn't always about absence. Sometimes it's about presence, about things that exist in ways we're only beginning to understand. The dark universe isn't empty or void. It's full of structure, full of energy, full of possibilities we're still learning to see. In the 1930s, astronomy was experiencing a golden age of discovery. Telescopes were revealing that our Milky Way was just one galaxy among many, that the universe was far larger than anyone had imagined. It was against this backdrop of cosmic expansion that a Swiss astronomer named Fritz Zwicky made an observation that would haunt cosmology for the rest of the century and beyond. Zwicky was not your typical astronomer. He was brilliant, eccentric, and often abrasive. He had a habit of calling his colleagues spherical bastards, because he said they were bastards no matter which way you looked at them. But despite his difficult personality, or perhaps because of it, Zwicky had an uncanny ability to see what others missed, to push ideas to their logical extremes and beyond. In 1933, Zwicky turned his attention to the Coma Cluster, a massive collection of over 1,000 galaxies located about 300 million light-years from Earth. The Coma Cluster is one of the nearest galaxy clusters to us, a cosmic metropolis where galaxies swarm through space, bound together by their mutual gravitational attraction. It's visible through a modest telescope as a faint concentration of fuzzy spots in the constellation Coma Berenices. But through the large telescopes of Zwicky's time, it revealed itself as something magnificent and puzzling. Zwicky wanted to understand how the cluster held together. It was a simple question with what should have been a simple answer. If you knew how much mass was in the cluster and how fast the galaxies were moving, you could determine whether the cluster was stable or flying apart. It was basic physics, no different in principle from calculating whether a rocket has enough speed to escape Earth's gravity. To measure the speeds of galaxies in the cluster, Zwicky used a technique called spectroscopy. When a galaxy moves toward us, its light gets compressed, shifting toward the blue end of the spectrum. When it moves away, the light stretches out, shifting toward the red. By measuring these shifts, Zwicky could determine how fast each galaxy was moving along our line of sight. It was like listening to the Doppler shift of a train whistle, but with light instead of sound. What he found was startling. The galaxies in the Coma Cluster were moving at enormous speeds, over 1,000 kilometers per second in some cases. That's fast enough to cross the entire United States in 4 seconds. At those speeds, the galaxies should have escaped the cluster's gravitational pull long ago, flying off into intergalactic space like sparks from a Catherine wheel. But they hadn't. The cluster was clearly stable, had been there for billions of years, would be there for billions more. The only way this made sense was if there was far more mass in the cluster than met the eye. Zwicky calculated that the cluster needed about 400 times more mass than he could see in stars, and gas to generate enough gravity to hold itself together. 400 times, not twice as much, not 10 times as much, but hundreds of times more mass than all the visible matter combined. It was such an outrageous number that Zwicky himself seemed somewhat stunned by it. He wrote about it in German, calling this missing mass dunkel materia, dark matter. The name was descriptive rather than explanatory. Zwicky didn't know what this dark matter was, only that it had to exist if the laws of physics were correct. He suggested various possibilities. Maybe it was cold gas that didn't glow. Maybe it was dust, planets, or dim stars. Maybe it was something more exotic. He even speculated about what he called gravitational drag, though he never fully developed this idea. What's remarkable about Zwicky's discovery is how clearly he saw its implications. He understood that if the coma cluster needed this much dark matter, then other clusters probably did too. He realized that dark matter might be a universal phenomenon, not just a peculiarity of one cluster. He even suggested that dark matter might affect the large-scale structure of the universe, decades before anyone else was thinking in such terms. But Zwicky's discovery was met with skepticism, and not just because of his personality. The idea that most of the universe's mass was invisible seemed too radical, too contrary to common sense. Many astronomers assumed there was something wrong with Zwicky's measurements or calculations. Perhaps the cluster wasn't in equilibrium. Perhaps the velocity measurements were incorrect. Perhaps there was some systematic error nobody had identified. There was also the problem of Zwicky's reputation. He was known for wild ideas, some brilliant, others bizarre. He coined the term supernova and correctly explained these stellar explosions. He predicted the existence of neutron stars decades before they were discovered. But he also proposed using nuclear explosions to propel spacecraft and suggested that tired light, not the expansion of space, might explain galactic redshifts. His colleagues never knew whether his latest idea would turn out to be prophetic or preposterous. So for years dark matter remained a curiosity, a puzzle that most astronomers filed away as interesting but probably wrong. Zwicky continued to advocate for it, continued to find evidence for it in other clusters, but the broader community remained unconvinced. It would take decades and completely independent lines of evidence before dark matter was taken seriously. Part of the problem was that Zwicky's observations were ahead of their time. The instruments of the 1930s and 1940s weren't precise enough to rule out conventional explanations. Maybe there really were vast numbers of dim stars or brown dwarfs that telescopes couldn't detect. Maybe there were extensive halos of hot gas that would only be visible in X-rays, which couldn't penetrate Earth's atmosphere. Without better data, dark matter remained a hypothesis rather than a discovery. But Zwicky never gave up on the idea. He spent years refining his measurements, studying more clusters, looking for additional evidence. He developed new techniques for measuring galaxy distances and velocities. He pioneered the use of gravitational lensing to map the distribution of matter in clusters, decades before technology made this practical. He was like a detective who had found a crucial clue but couldn't convince anyone else of its importance. What makes Zwicky's story particularly poignant is that he lived to see the beginning of dark matter's acceptance, but died just before it became mainstream. By the 1970s, new evidence from galaxy rotation curves was confirming what Zwicky had found in clusters. But Zwicky died in 1974, just as the dark matter revolution was beginning. He knew he had been right, but he never saw the full vindication of his discovery. Looking back, Zwicky's discovery of dark matter represents one of those moments when observation outpaces understanding. He saw something that didn't fit the existing picture of the universe, and had the courage to say so, even when it made him unpopular. He didn't know what dark matter was, couldn't prove it existed, but he knew the universe was telling him something important through those speeding galaxies in the coma cluster. The numbers Zwicky calculated have been refined over the decades. Modern measurements suggest the ratio of dark to ordinary matter in clusters is closer to 5 or 6 to 1, rather than 400 to 1. But the fundamental discovery remains unchanged. Most of the matter in galaxy clusters is invisible. Zwicky saw this first, saw it clearly, and spent much of his career trying to make others see it too. His discovery method was elegantly simple. Take what you can observe, the motions of galaxies. Apply the laws of physics, gravity and orbital mechanics. Find the discrepancy, too much speed for too little visible mass. Conclude that there must be invisible mass. It's a line of reasoning so straightforward that once you see it, you wonder how it could be wrong. And yet it took decades for the scientific community to accept it. Zwicky's dark matter was born from careful observation and simple physics, but it opened a door to questions that still challenge us today. What is this invisible matter? Why does it only interact gravitationally? How does it shape the universe we see? These questions have spawned thousands of research papers, dozens of experiments, and countless hours of observation and calculation. In many ways, we're still living in the shadow of Zwicky's discovery. Every search for dark matter particles, every map of the cosmic web, every simulation of galaxy formation builds on that first observation of galaxies moving too fast in the Coma cluster. Zwicky saw a problem that nobody else recognized as important, and that problem has become one of the defining challenges of modern physics. The story of Fritz Zwicky and dark matter is a reminder that the universe's biggest secrets often announce themselves quietly. They don't arrive with fanfare, but with small discrepancies, with numbers that don't quite match, with behaviours that don't quite make sense. It takes a special kind of mind to notice these discrepancies and an even more special kind of courage to insist they matter when everyone else thinks you're wrong. If Fritz Zwicky opened the door to dark matter, it was Vera Rubin who walked through it and showed everyone what was on the other side. Her story is one of persistence, precision, and the power of careful observation to reveal fundamental truths about the universe. Vera Cooper Rubin faced obstacles from the very beginning of her astronomical career. In the 1940s and 1950s, when she was starting out, astronomy was almost exclusively a man's field. Princeton wouldn't accept women into their astronomy graduate program. Palomar Observatory, home to some of the world's best telescopes, didn't allow women observers until 1965. When Rubin was pregnant with her first child, her advisor told her to find something else to do with her life. But Rubin loved the stars too much to give up. She had been fascinated by astronomy since childhood, watching the stars wheel across the sky from her bedroom window. She built her own telescope with her father's help, a cardboard tube with a lens at one end. She knew from age 10 that she wanted to be an astronomer, and no amount of discouragement could change her mind. Her path to discovering dark matter began with what seemed like a simple project: measuring how galaxies rotate. In the 1970s, Rubin and her colleague Kent Ford set out to study the rotation of spiral galaxies, those magnificent pinwheels of stars that grace so many astronomy photographs. They wanted to understand how stars at different distances from the galactic centre moved around their orbits. The expectation was straightforward. Galaxies should rotate like the solar system. Mercury, close to the Sun, whips around its orbit in just 88 days. Earth takes a year. Pluto, far from the Sun's gravitational grip, takes 248 years. The farther you go from the centre of mass, the slower things should move. This is basic orbital mechanics, as true for galaxies as for planets. To measure how galaxies rotated, Rubin and Ford used a special instrument Ford had built, an image tube spectrograph that could detect very faint light. They would point their telescope at a galaxy, align the spectrograph slit along the galaxy's disk, and measure the Doppler shift of light at different distances from the centre. One side of the galaxy would be moving toward them, its light slightly blue-shifted. The other side would be moving away, red-shifted. By measuring these shifts, they could determine how far stars were orbiting at different radii. Their first target was the Andromeda Galaxy, our nearest large galactic neighbour. It's a spectacular spiral galaxy, visible to the naked eye on dark nights, as a faint, fuzzy patch in the constellation Andromeda. Through a telescope, it reveals itself as a vast disk of stars, gas and dust, viewed at a slight angle from Earth. It was perfect for Rubin's study. What Rubin and Ford found was completely unexpected. As they measured stellar velocities farther and farther from Andromeda's centre, the speeds didn't drop off as predicted. Instead of declining like planetary orbits, the rotation speed stayed roughly constant all the way to the visible edge of the galaxy. Stars at the galaxy's periphery were moving just as fast as stars halfway out. This was impossible according to the visible distribution of matter. The bright central bulge of the galaxy contained most of the visible mass. Stars far from this centre should be moving much slower. It was like finding that Pluto orbited the Sun as fast as Mercury, defying everything we know about gravity and orbital motion. At first, Rubin thought there might be something wrong with their measurements. Science is full of systematic errors, instrumental quirks, and mistaken assumptions that can lead to false results. They checked and rechecked their data, calibrated and recalibrated their instruments, but the result remained the same. The galaxy was rotating all wrong. So they looked at another galaxy and another and another. Every spiral galaxy they examined showed the same pattern. Flat rotation curves extending far beyond the visible stars. It wasn't a peculiarity of Andromeda or a measurement error. It was a universal phenomenon. Spiral galaxies simply didn't rotate the way they should based on their visible matter. The implications were staggering. For the galaxies to rotate this way, they needed much more mass in their outer regions than anyone could see. This invisible mass had to be distributed in a vast halo extending far beyond the visible stars, perhaps 10 times farther. Each galaxy was embedded in a cocoon of dark matter, like a ship in a bottle made of invisible glass. Rubin calculated that galaxies contained about 6 times more dark matter than ordinary matter. This was remarkably consistent with what Zwicky had found in galaxy clusters decades earlier, though arrived at through completely different observations. Dark matter wasn't just holding clusters together, it was shaping individual galaxies too. But Rubin's discovery went beyond confirming dark matter's existence. Her rotation curves revealed how dark matter was distributed. It wasn't concentrated in the centre like visible matter, but spread out in an enormous halo. This distribution was crucial for understanding how galaxies formed and evolved. The dark matter halo came first, its gravity pulling in ordinary matter to form the stars and gas we see. The beauty of Rubin's work was its directness. She wasn't inferring dark matter from complex calculations or statistical analyses. She was seeing its gravitational signature directly in the motion of stars. Every rotation curve was like a fingerprint of the dark matter halo, unique to each galaxy, but following the same general pattern. Initially, the astronomical community was skeptical. Alternative explanations were proposed. Maybe there was something wrong with Newton's laws at galactic scales. Maybe galaxies contained vast numbers of dim red dwarf stars or brown dwarfs that couldn't be seen. Maybe there were extensive halos of hot gas that hadn't been detected yet. But as more data accumulated, these alternatives fell away. Radio observations of hydrogen gas in galaxies showed the same flat rotation curves extending even farther than the stars. X-ray observations ruled out hot gas halos massive enough to explain the rotation. Careful star counts showed there weren't nearly enough dim stars to account for the missing mass. Rubin herself was cautious about interpreting her results. She preferred to talk about missing mass rather than dark matter, focusing on the observational facts rather than theoretical interpretations. She would present her rotation curves and let others draw conclusions. But the conclusion was inescapable. Galaxies were dominated by invisible matter. What made Rubin's work particularly convincing was its scope. She and her colleagues eventually measured rotation curves for more than 200 galaxies of all types and sizes. Every single one showed evidence of dark matter. It wasn't a quirk of a few galaxies, it was a universal property. The universe was fundamentally different from what astronomers had believed. Rubin's discovery transformed dark matter from a controversial hypothesis to an accepted fact. After her work, the question was no longer whether dark matter existed, but what it was made of. Her rotation curves became the gold standard for dark matter detection, reproduced in textbooks and taught to every astronomy student. But Rubin's contribution went beyond the scientific. As one of the few prominent female astronomers of her generation, she became a role model and advocate for women in science. She mentored young female astronomers, fought for equal access to telescopes and facilities, and showed by example that women could make fundamental discoveries about the universe. She often spoke about the night she was first allowed to use the Palomar Observatory telescope in 1965. There was no women's bathroom in the dome, so she cut out a paper skirt and pasted it on the figure on the men's room door. It was a small act of rebellion, but it symbolized her approach. Don't wait for permission. Don't accept arbitrary barriers. Just do the science. Rubin's rotation curves did more than reveal dark matter. They revealed the universe's hidden architecture. Every galaxy we see is just a luminous tip of a much larger dark matter structure. The beautiful spiral arms, the glowing nebulae, the billions of stars, all of this is just decoration on an invisible framework. We live in a galaxy that is mostly dark, orbiting within a halo we cannot see, held in place by matter we don't understand. The flat rotation curves Rubin discovered have become one of the most important pieces of evidence for dark matter. They're so universal, so consistent, that any alternative theory must explain them. They've been confirmed by observations spanning the electromagnetic spectrum, from radio waves to X-rays. They've been found in galaxies billions of light years away, showing that dark matter has dominated galaxies throughout cosmic history. Rubin continued observing galaxies well into her 80s, accumulating more data, refining measurements, always pushing for better understanding. She never won a Nobel Prize, though many felt she deserved one. She died in 2016, having transformed our understanding of the universe, but still wondering, like all of us, what dark matter actually is. Her legacy lives on in every observation of galaxy dynamics, every search for dark matter particles, every simulation of cosmic structure formation. She showed us that the universe is far stranger than it appears, that most of reality is invisible, and that careful observation can reveal truths that theory alone might never find. Vera Rubin's story reminds us that the universe's biggest mysteries often hide in plain sight. The rotation of galaxies had been observed for decades before Rubin, but nobody had looked carefully enough to see the problem. It took patience, precision, and persistence to reveal that galaxies were telling us something profound about the nature of reality. Now that we knew dark matter existed, shaped galaxies, and held clusters together, the next question became obvious and urgent. What is it? This question has driven thousands of physicists, astronomers, and cosmologists for decades, spawning elaborate experiments, exotic theories, and a frustrating series of non-detections that have only deepened the mystery. The challenge of identifying dark matter is unlike anything else in physics. Usually when scientists discover a new phenomenon, they can isolate it, experiment with it, measure its properties directly, but dark matter refuses to cooperate. It doesn't emit light, doesn't absorb light, doesn't reflect light. It passes through ordinary matter like a ghost, leaving only gravitational footprints. How do you catch something that barely exists in our reality? Scientists began by listing what dark matter couldn't be. It couldn't be ordinary atoms because we would see them. It couldn't be antimatter because antimatter annihilates with matter in spectacular bursts of energy, and we don't see those bursts. It couldn't be black holes in the quantities needed because their gravitational lensing effects would be obvious. Through elimination, researchers concluded that dark matter had to be something fundamentally different from anything in the standard model of particle physics. This realization was both exciting and daunting. Exciting because it meant there was new physics to discover, particles and forces beyond our current understanding. Daunting because it meant searching for something without knowing what you're looking for, like trying to catch a fish without knowing if it lives in water, air, or some medium we haven't imagined. The leading candidates for dark matter became known as WIMPs, weakly interacting massive particles. The name is partly descriptive and partly hopeful. These hypothetical particles would have mass, hence their gravitational effects, but would interact with ordinary matter only through the weak nuclear force, making them nearly impossible to detect. They would have been created in the hot, dense early universe and survived to the present day, relics of the Big Bang floating invisibly through space. WIMPs were attractive candidates for several reasons. Particle physics theories that try to extend the standard model, particularly supersymmetry, naturally predicted particles with just the right properties to be dark matter. The calculated abundance of these particles from the early universe matched remarkably well with the observed amount of dark matter. This coincidence, sometimes called the WIMP miracle, seemed too good to be mere chance. To search for WIMPs, scientists built detectors in the deepest, quietest places on Earth. The problem with detecting dark matter is that even if it occasionally interacts with ordinary matter, these interactions are extraordinarily rare and weak. Cosmic rays, radioactivity, even the vibrations from trucks driving nearby could swamp any dark matter signal. So researchers went underground. Deep beneath mountains, in abandoned mines, in tunnels far from the surface, scientists constructed some of the most sensitive instruments ever built. These detectors typically consisted of ultra-pure materials, xenon, germanium, silicon, cooled to near absolute zero and surrounded by shields of lead, water and rock. The idea was simple. If a dark matter particle happened to bump into an atomic nucleus in the detector, it would deposit a tiny amount of energy that could be measured. The xenon experiment, buried under a mountain in Italy, uses tons of liquid xenon as its detection medium. When a particle interacts with a xenon nucleus, it produces a flash of light and releases electrons. By measuring both signals, scientists can determine what kind of particle caused the interaction. The detector is so sensitive it can measure the energy equivalent of a mosquito landing on your hand, but distributed over a single atom. The LUX experiment, located nearly a mile underground in a former gold mine in South Dakota, follows a similar principle, but with different detection techniques. The cryogenic dark matter search uses semiconductor crystals cooled to within a fraction of a degree of absolute zero, measuring both the heat and electrical signal from particle interactions. These experiments are marvels of engineering and patience. Scientists spend years eliminating every possible source of background noise, calibrating their detectors with known particles, and waiting for the telltale sign of dark matter. It's like listening for a whisper in a hurricane, requiring not just sensitive instruments, but incredible dedication and faith that the signal exists. But after decades of searching, WIMPs remain elusive. Experiment after experiment has pushed the sensitivity lower, ruling out larger and larger portions of the theoretical parameter space where WIMPs might hide, but no confirmed detection has been made. Each non-detection narrows the possibilities but also raises uncomfortable questions. Are WIMPs the wrong answer? Are we looking in the wrong way? Or are we just not sensitive enough yet? While underground detectors search for dark matter directly, other experiments look for indirect evidence. If dark matter particles can annihilate with each other, they should produce standard model particles that we can detect. Gamma rays, neutrinos, positrons. These could all be signatures of dark matter annihilation, happening in regions where dark matter is dense, like the centers of galaxies or the Sun. The Fermi Gamma Ray Space Telescope scans the sky for excess gamma rays that might come from dark matter. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometre of Antarctic ice to detect high-energy neutrinos that could originate from dark matter annihilation in the Sun or the galactic centre. The Alpha Magnetic Spectrometer on the International Space Station measures cosmic ray particles, looking for anomalies that might indicate dark matter. These indirect searches have found some intriguing hints: an excess of gamma rays from the galactic centre, more positrons than expected in cosmic rays, unusual signals from dwarf galaxies. Each of these could potentially be explained by dark matter, but they could also be explained by more mundane astrophysical processes like pulsars or cosmic ray interactions. Without a smoking gun, the evidence remains tantalizingly ambiguous. Another approach is to try to create dark matter particles in laboratory collisions. The Large Hadron Collider, the world's most powerful particle accelerator, smashes protons together at energies approaching those of the early universe. If dark matter particles can be produced in these collisions, they would escape the detector without being seen, carrying away energy and momentum. Scientists look for events where energy seems to disappear, where the books don't balance, as a sign that dark matter might have been created. The LHC has searched extensively for signs of dark matter production, looking for missing energy in collision events, searching for supersymmetric particles, hunting for any deviation from standard model predictions. So far, nothing conclusive has emerged. The energies might not be high enough, or dark matter might not couple to standard model particles in the way theories predict. As WIMPs have proven more elusive than hoped, scientists have broadened their search to consider other possibilities. Perhaps dark matter isn't made of WIMPs at all, but something else entirely. The range of candidates spans an enormous range of masses and properties, from ultralight particles to massive primordial black holes. Axions represent another major category of dark matter candidates. These hypothetical particles would be much lighter than WIMPs, perhaps a billionth the mass of an electron, or even less. They were originally proposed to solve a different problem in particle physics, the strong CP problem, but they could also be dark matter. If axions exist, they would be so light and numerous that they would behave less like individual particles and more like a cosmic field permeating all of space. Searching for axions requires completely different techniques from WIMP searches. The Axion dark matter experiment uses powerful magnetic fields and microwave cavities to try to convert axions into photons that can be detected. It's like tuning a radio to find the station where dark matter broadcasts, except we don't know the frequency and the signal is unimaginably weak. The concept behind axion detection is beautiful in its cleverness. In a strong magnetic field, axions should occasionally convert into photons, particles of light. By creating the strongest magnetic fields possible and listening with the most sensitive microwave receivers ever built, scientists hope to catch these conversion events. The experiment must scan through millions of possible frequencies, spending weeks at each one, searching for the faint excess of photons that would signal axion dark matter. At the other extreme of the mass scale, some scientists wonder if dark matter might be primordial black holes. Black holes formed not from collapsing stars, but from dense regions in the early universe. These black holes could range from microscopic to stellar masses, and if they were numerous enough, they could account for dark matter. The search for primordial black holes uses gravitational lensing. When a black hole passes between us and a distant star, it can magnify the star's light briefly. By monitoring millions of stars simultaneously, astronomers look for these microlensing events. Some have been found, but not nearly enough to account for all dark matter. Still, primordial black holes might make up a portion of the dark matter, adding another layer to the mystery. There are even more exotic proposals: sterile neutrinos, hypothetical cousins of regular neutrinos that don't interact through any force except gravity. Q-balls, stable configurations of scalar fields left over from the early universe. Superfluid dark matter that exhibits quantum behavior on galactic scales. Dark atoms made of dark protons and dark electrons that interact through dark electromagnetism. Each theory has its advocates, its experimental signatures, its dedicated searches. The proliferation of dark matter candidates reflects both the richness of theoretical physics and our ignorance about what dark matter actually is. It's humbling to realize that after decades of searching, we can't even narrow it down to a single category of particle. Dark matter could be one thing or many things. Different types of dark matter might dominate in different environments or at different times in cosmic history. Some scientists have begun to wonder if we're approaching the problem wrong. Perhaps dark matter doesn't interact with ordinary matter at all, except through gravity. If that's true, we might never detect it directly, only infer its properties from its gravitational effects. This possibility is deeply unsatisfying to physicists who are used to taking things apart to see how they work, but it might be the reality we have to accept. There's also the uncomfortable possibility that dark matter is telling us our theories are wrong. Modified Newtonian dynamics, or MOND, proposes that gravity behaves differently at very low accelerations, like those at the edges of galaxies. In this view, there is no dark matter, just a modification to gravity that creates the illusion of missing mass. While MOND can explain some observations, particularly galaxy rotation curves, it struggles with others, like gravitational lensing and the cosmic microwave background. The search for dark matter has become one of the most elaborate and expensive scientific endeavours of our time. Billions of dollars have been spent on detectors, accelerators, telescopes, and satellites. Thousands of scientists have dedicated their careers to finding these elusive particles. And yet dark matter remains as mysterious as when Zwicky first noticed those speeding galaxies in the Coma cluster. This might seem like failure, but it's actually how science progresses. Each non-detection teaches us something. Each ruled-out possibility narrows the search space. Each new experimental technique opens windows we couldn't look through before. The history of physics is full of particles that took decades to find after they were predicted. The neutrino, the Higgs boson, gravitational waves. Dark matter might simply require more patience, better technology, or a fundamentally new approach. The challenge of dark matter has also pushed technology to extraordinary limits. The detectors built to search for dark matter are among the most sensitive instruments ever created. The computational techniques developed to analyze the data have applications far beyond physics. The international collaborations formed to tackle this problem have created new models for how big science can be organized and funded. Meanwhile, astronomers continue to map dark matter's distribution throughout the universe, using gravitational lensing to see the invisible. These maps reveal the cosmic web in stunning detail, vast filaments of dark matter stretching between galaxies, dense knots where clusters form, voids where little matter of any kind exists. Even if we don't know what dark matter is, we're getting better at understanding what it does. The hunt for dark matter represents science at its most ambitious and uncertain. We're searching for something we've never seen, something that might not interact with our world in any way we can measure, something that challenges our understanding of what matter itself means. It's a quest that might take generations to complete, or might be resolved tomorrow with a single detection. That uncertainty, that possibility of discovery, keeps thousands of scientists working late into the night, checking their data one more time, hoping to be the first to glimpse the universe's hidden reality. When you look at the night sky, the stars seem randomly scattered, like salt spilled across black velvet. But zoom out far enough, survey millions of galaxies across billions of light years, and a pattern emerges that takes your breath away. Galaxies aren't distributed randomly at all. They're organized into a vast cosmic web, a network of filaments and voids that spans the entire observable universe. And the architect of this magnificent structure is dark matter. The cosmic web is one of the universe's most beautiful and profound features. Imagine a three-dimensional spider web the size of the universe, but instead of silk, the strands are made of dark matter and galaxies. These filaments can stretch for hundreds of millions of light years, connecting clusters of galaxies like highways between cosmic cities. Between the filaments are voids, vast empty regions containing few galaxies, some so large you could fit 1,000 Milky Ways inside with room to spare. This structure didn't exist at the beginning. When the universe was young, matter was distributed almost perfectly uniformly, with only the tiniest variations in density from place to place. These variations, no more than 1 part in 100,000, were the seeds from which all structure would grow. But how did such small seeds grow into the cosmic web we see today? The answer is dark matter, and the story of how it shaped the universe is one of the most elegant in all of cosmology. Dark matter began clumping before ordinary matter could. In the early universe, the ordinary matter we're made of was coupled to light through electromagnetic interactions. This coupling prevented ordinary matter from collapsing under its own gravity. The pressure from photons kept pushing it apart. But dark matter doesn't interact with light. It was free to start clumping from the very beginning, pulled together by gravity with nothing to resist it. Think of it like this. Imagine trying to build a sandcastle while waves keep washing over the beach. The sand gets scattered each time a wave hits. But if you could first build an invisible framework that the waves pass right through, you could pack sand around that framework once the tide goes out. Dark matter was that invisible framework, creating gravitational wells that ordinary matter would later fall into. By the time the universe was about 400,000 years old and cool enough for atoms to form, dark matter had already created a network of dense regions and connecting filaments. When ordinary matter finally decoupled from light, it fell into these pre-existing dark matter structures, like water flowing into valleys. The cosmic web was dark matter's blueprint, and ordinary matter simply followed the plan. Computer simulations of the universe's evolution reveal this process in stunning detail, starting with the tiny density fluctuations observed in the cosmic microwave background. These simulations use the laws of physics to calculate how matter moves and clumps over billions of years. They require some of the world's most powerful supercomputers, tracking the gravitational interactions of trillions of particles over cosmic time. The results are remarkable. The simulated cosmic web looks exactly like the real one we observe. The same filamentary structure, the same distribution of cluster sizes, the same vast voids. But here's the crucial point. These simulations only work if dark matter dominates. Try to form the cosmic web with ordinary matter alone, and you fail completely. The structures don't form fast enough, don't match observations, don't create the universe we see. The formation of the cosmic web follows a hierarchy. First, small clumps of dark matter merge to form larger ones. These grow by pulling in more dark matter from their surroundings and by merging with other clumps. The largest clumps become the sites of galaxy clusters. Smaller clumps host individual galaxies. The very smallest might contain no visible matter at all. Dark matter, halos with no stars, invisible except for their gravitational effects. This hierarchical structure formation means that galaxies didn't form all at once. The first galaxies were small, formed in the densest peaks of the dark matter distribution when the universe was only a few 100 million years old. These early galaxies merged and grew, fed by streams of gas flowing along dark matter filaments. The largest galaxies we see today are the products of countless mergers, cosmic cannibalism guided by dark matter's invisible hand. The filaments of the cosmic web are like cosmic highways along which matter flows. Gas streams along these filaments, feeding galaxies with fresh material for star formation. Galaxies themselves move along filaments, drawn toward the massive clusters at filament intersections. When we map the positions and velocities of galaxies, we can see this flow, a cosmic river system with dark matter as the riverbed. Gravitational lensing has allowed us to map the dark matter web directly. When light from distant galaxies passes through the cosmic web, it gets deflected by the gravity of dark matter, creating subtle distortions in galaxy shapes. By measuring these distortions for millions of galaxies, astronomers can reconstruct the three-dimensional distribution of dark matter between us and the distant universe. These dark matter maps are revelatory. They show that every galaxy cluster is connected to others by dark matter bridges. They reveal dark matter clumps with no associated galaxies, failed galaxies that never accumulated enough gas to form stars. They confirm that the cosmic web is mostly dark, with visible matter just trace contamination in a dark matter universe. The cosmic web also explains why the universe looks different at different scales. On small scales, planets, stars, even galaxies, gravity has had time to create complex collapsed structures. On the largest scales, bigger than a few 100 million light years, the universe still looks smooth, the primordial density fluctuations not yet grown into structures. The cosmic web exists at the sweet spot between these extremes, large enough to show the universe's structure, but small enough that gravity has had time to work. One of the most amazing features of the cosmic web is its voids. These aren't truly empty. They contain some galaxies and are filled with dark matter and gas, but they're dramatically underdense compared to the filaments and clusters. The largest voids are almost 1 billion light years across, so large that if you were in the centre of one, you might think the universe was nearly empty. Voids grow because of the same gravitational instability that creates clusters, just in reverse. Regions that start out slightly underdense lose matter to their denser surroundings, becoming ever emptier. It's like a gravitational rich-get-richer scenario. Dense regions pull in more matter and become denser, while underdense regions lose matter and become more void-like. The cosmic web isn't static. It's evolving, growing, changing. Filaments are thickening as more matter flows onto them. Clusters are growing at filament intersections. Voids are expanding, pushing galaxies onto their surfaces. The web today looks different from the web 5 billion years ago, and it will look different 5 billion years from now. This evolution is accelerating due to dark energy, which we'll explore later. As dark energy pushes the universe apart, it's stretching the cosmic web, making voids larger and filaments thinner. Eventually, dark energy will win. stopping structure formation and freezing the cosmic web in place. But for now, the web continues to evolve, a dynamic sculpture shaped by the competing forces of dark matter's pull and dark energy's push. The cosmic web also influences galaxy evolution. Galaxies in dense cluster environments evolve differently from those in voids. Cluster galaxies tend to be elliptical, their star formation long ago shut down by interactions with other galaxies and the cluster environment. Void galaxies tend to be spiral, still forming stars evolving in isolation. A galaxy's position in the cosmic web determines its fate. Even our own Milky Way's position in the cosmic web affects us. We're not in a cluster or a void, but in a filament, part of a structure called the local sheet. Our nearest large neighbour, Andromeda, is approaching us along this filament, and in about 4 billion years, our galaxies will merge. This future collision is programmed into the cosmic web, as inevitable as water flowing downhill. The cosmic web teaches us that structure in the universe is not random, but follows patterns set by dark matter and the laws of physics. Every galaxy's position, every cluster's mass, every void's size was determined by tiny quantum fluctuations in the infant universe, amplified by dark matter's gravity over billions of years. We live in a structured universe, and dark matter is the structure's foundation. When we study the cosmic web, we're seeing dark matter's masterpiece. It's a structure so large that light takes billions of years to cross it, yet so detailed that every galaxy has its place. It's mostly invisible, yet it determines everything we see. It's ancient, dating back almost to the Big Bang, yet still growing and changing. The cosmic web is dark matter's gift to the universe, the scaffolding on which all visible beauty hangs. Just when astronomers were getting comfortable with dark matter, the universe threw them another curveball. This one was even stranger, even more unexpected, and it would fundamentally change our understanding of cosmic destiny. The discovery came from studying stellar explosions billions of light years away, and it revealed that not only was most of the universe's matter invisible, but most of its energy was too. The story begins with supernovae, specifically a type called Type Ia. These stellar explosions are among the most violent events in the universe. In a matter of seconds, a white dwarf star can release more energy than our sun will produce in its entire 10 billion year lifetime. The explosion is so bright it can outshine an entire galaxy, visible across billions of light years of space. What makes Type Ia supernovae special for cosmology is their consistency. They all explode with roughly the same power, making them what astronomers call standard candles. If you know how bright something truly is and measure how bright it appears, you can calculate its distance. It's like seeing a car's headlights at night. If you know how bright headlights are, you can estimate how far away the car is by how dim they appear. In the 1990s, 2 teams of astronomers set out to use Type Ia supernovae to measure how the universe's expansion was slowing down. Everyone knew the universe was expanding. Edwin Hubble had discovered that in the 1920s. And everyone knew that gravity should be slowing this expansion. The only question was by how much. Would gravity eventually stop the expansion and cause the universe to collapse? Or would the universe expand forever, just more and more slowly? The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, began searching for distant supernova. They developed techniques to find these explosions quickly, measure their brightness precisely, and determine their distances accurately. It was painstaking work, requiring coordination between telescopes around the world and in space. Finding distant supernova is like finding a needle in a haystack, while the haystack is changing. Astronomers would image the same patches of sky weeks apart, then use computers to subtract one image from another. Any new point of light could be a supernova, but it could also be an asteroid, a variable star, or some other transient phenomenon. Each candidate had to be verified, its spectrum measured to confirm it was truly a Type Ia supernova. The teams expected to find that distant supernova were brighter than their redshifts suggested they should be. This would indicate that the universe's expansion was slowing, that these supernovae exploded when the universe was expanding faster, and are therefore closer than they would be in a uniformly expanding universe. The question was just how much brighter they would be. But when the data came in, both teams found something shocking. The distant supernovae weren't brighter than expected. They were dimmer, about 25% dimmer than they should be if the universe's expansion was slowing down. The only explanation that made sense was almost unthinkable. The universe's expansion wasn't slowing down at all. It was speeding up. Imagine throwing a ball into the air and watching it slow down, stop, and then suddenly accelerate upward, flying faster and faster into the sky. That's essentially what the universe was doing. Sometime in the last 5 billion years, the expansion of space switched from deceleration to acceleration. Galaxies weren't just moving apart, they were moving apart faster and faster. Both teams spent months checking their results, looking for systematic errors, alternative explanations, anything that could explain away this impossible observation. Maybe distant supernovae were intrinsically dimmer than nearby ones. Maybe dust was absorbing their light. Maybe there was some selection bias in which supernovae they could detect. But every test confirmed the original result. The universe was accelerating. The implications were staggering. For the universe to accelerate, there had to be some force opposing gravity, some kind of anti-gravity that pushed things apart rather than pulling them together. This force had to be strong enough to overcome the gravitational attraction of all the matter in the universe, dark and ordinary combined, and it had to be growing stronger over time, or at least maintaining its strength while matter's gravity weakened as the universe expanded. Scientists called this mysterious force dark energy. Dark because, like dark matter, it was invisible, and energy because it had to be a form of energy to cause acceleration. But unlike dark matter, which clumps and creates structure, dark energy seems to be smooth, filling all of space uniformly. It's like an invisible fluid that permeates everything, pushing space apart from within. The discovery was so unexpected, so paradigm-shifting, that many scientists initially refused to believe it. But as more supernovae were observed, as different teams confirmed the results, as other lines of evidence emerged, the reality of dark energy became undeniable. In 2011, Perlmutter, Schmidt, and Riss were awarded the Nobel Prize in Physics for their discovery. But what is dark energy? This question makes the mystery of dark matter look simple by comparison. At least with dark matter, we understand what matter is, even if this particular type is invisible. With dark energy, we're dealing with something that seems to violate our intuitions about how energy behaves. The leading explanation, if you can call it that, is that dark energy is a property of space itself. Even completely empty space, devoid of all matter and radiation, has an intrinsic energy density. This vacuum energy, or cosmological constant, creates a kind of negative pressure that causes space to expand. The more space expands, the more vacuum energy there is, causing even faster expansion. This idea actually goes back to Einstein. When he first developed general relativity, he added a term called the cosmological constant to his equations. He needed it to create a static universe. At the time, everyone thought the universe was eternal and unchanging. When Hubble discovered the universe was expanding, Einstein called the cosmological constant his biggest blunder and removed it. But with the discovery of dark energy, the cosmological constant was back. Not to keep the universe static, but to make it accelerate. The amount of dark energy is mind-boggling. It makes up about 68% of the universe's total energy density. Dark matter makes up about 27%. Everything else, all the stars, planets, gas, dust, black holes, all the ordinary matter and energy we're familiar with, makes up just 5%. We're not just a minority in the universe. We're a rounding error. Dark energy's density is incredibly small, but incredibly important. It's equivalent to about 4 hydrogen atoms per cubic meter of space. That seems negligible, but integrated over the entire universe, it dominates everything else. And unlike matter, which gets diluted as space expands, dark energy's density stays roughly constant. As the universe expands, new space comes with its own dark energy, maintaining the density even as the volume grows. This constant density is one of dark energy's most puzzling features. As the universe expands, matter density decreases. The same amount of matter in a larger volume means lower density. Radiation density decreases even faster. But dark energy's density stays the same, which means the total amount of dark energy in the universe is increasing. Where does this energy come from? How does it not violate conservation of energy? These questions touch on the deepest mysteries of physics. The discovery of dark energy completely changed our picture of the universe's past and future. Looking backward, we now know that dark energy was negligible in the early universe when matter density was much higher. The universe transitioned from matter-dominated to dark energy-dominated about 5 billion years ago, around the time our solar system was forming. We happen to live at a special time when we can see both eras. Looking forward, the future is dark indeed. As dark energy continues to dominate, the universe will expand faster and faster. Galaxies will fly apart from each other, eventually moving away faster than light can travel between them. The observable universe will shrink as distant galaxies disappear beyond the cosmic horizon. In the far future, perhaps 100 billion years from now, observers in our galaxy, which by then will have merged with Andromeda, will see only darkness beyond, unaware that billions of other galaxies exist. This fate, sometimes called the Big Freeze or heat death, is profoundly different from what scientists expected before dark energy's discovery. Instead of eventually collapsing in a big crunch or expanding forever but ever more slowly, the universe will expand faster and faster, growing cold, dark and empty. It's a lonely future, but one that won't arrive for trillions of years. The discovery of dark energy also raised profound questions about why the universe is the way it is. The observed value of dark energy density is bizarrely small compared to theoretical predictions. Quantum field theory suggests that vacuum energy should be at least 1060 times larger than what we observe, possibly as much as 10 Maha 120 times larger. This discrepancy, called the cosmological constant problem, is one of the worst mismatches between theory and observation in all of science. If dark energy were as large as theory predicts, the universe would have blown apart before atoms could form, let alone stars, galaxies, and life. The fact that dark energy is precisely small enough to allow structure to form, but large enough to be detected now, seems like an impossible coincidence. It's led some scientists to invoke the anthropic principle. We observe this value because any other value wouldn't allow observers to exist. Dark energy isn't just mysterious, it's mysterious in a way that challenges our fundamental understanding of physics. With dark matter, we at least have analogies. It's matter, just a type we can't see. But dark energy seems to violate our basic intuitions about how the universe works. It's a force that grows stronger as things get farther apart, energy that appears from nowhere, a property of nothingness itself. To understand how strange dark energy is, consider what we normally expect from forces in energy. Gravity gets weaker with distance. Electromagnetic forces dissipate as they spread out. Energy is conserved. It can change forms but can't be created or destroyed. These principles have guided physics for centuries. Dark energy seems to break all these rules. The simplest explanation for dark energy is that it's a cosmological constant, an intrinsic property of space-time itself. In this view, every cubic meter of space has the same tiny amount of dark energy, always and forever. This energy creates negative pressure. Instead of pushing outward like gas pressure, it pulls inward on itself while pushing space apart. It's counterintuitive, but it's what the mathematics of general relativity predicts. But the cosmological constant has serious problems. The biggest is the fine-tuning problem we mentioned earlier. When physicists calculate what the vacuum energy should be using quantum mechanics, they get a number that's catastrophically wrong. It's not just off by a factor of 2 or 10 or even a million. It's off by more than the number of atoms in the observable universe. No other calculation in physics is so spectacularly incorrect. This mismatch suggests we're missing something fundamental about quantum mechanics, gravity, or both. Perhaps there's some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny residual we observe. Perhaps our calculation is wrong in some basic way. Perhaps the vacuum energy is exactly zero, and what we call dark energy is something else entirely. Each possibility opens up new mysteries. Another possibility is that dark energy isn't constant but changes over time. This idea, called quintessence, proposes that dark energy is a dynamic field that evolves as the universe expands. Unlike the cosmological constant, which is the same everywhere and always, quintessence could vary in space and time, perhaps being stronger in the past or future. Quintessence gets its name from the ancient Greek concept of a fifth element beyond earth, air, fire, and water, the substance that filled the heavens. In modern physics, quintessence would be a scalar field, similar to the Higgs field, but much lighter and more weakly interacting. This field would have potential energy that drives cosmic acceleration, but the amount of energy could change as the field evolves. If dark energy is quintessence, it opens up fascinating possibilities. The acceleration of the universe might be temporary, eventually slowing or even reversing. Dark energy might have been different in the early universe, affecting how structures formed. It might even interact with matter in subtle ways we haven't detected yet. Some theories suggest quintessence could clump slightly, creating variations in the acceleration rate across the universe. Testing whether dark energy is constant or changing requires incredibly precise measurements over cosmic time. Astronomers measure the expansion rate at different epochs using various techniques: supernovae for recent times, Baryon acoustic oscillations for intermediate times, the cosmic microwave background for early times. So far, all measurements are consistent with a cosmological constant, but the error bars are still large enough to allow for quintessence. There are even more exotic possibilities. Perhaps dark energy is a sign that general relativity is wrong on cosmic scales. Just as Newton's gravity had to be modified by Einstein to explain Mercury's orbit, perhaps Einstein's gravity needs modification to explain cosmic acceleration. These modified gravity theories can reproduce the effects of dark energy without invoking any new energy at all. Modified gravity theories come in many flavors. Some add extra terms to Einstein's equations that become important only on large scales. Others propose that gravity leaks into extra dimensions we can't see, weakening its effect over cosmic distances. Still others suggest that what we interpret as acceleration is actually an illusion caused by our position in the universe, or the way we measure distances. Testing modified gravity is challenging because these theories are often designed to match general relativity in all current observations, while differing only in subtle ways. But there are differences. Modified gravity should affect how structures grow differently than dark energy would. It might create variations in the gravitational constant at different scales or times. It might produce gravitational waves with different properties than general relativity predicts. Another radical idea is that dark energy is related to the multiverse, the hypothetical ensemble of multiple universes beyond our own. In this view, different universes have different values of dark energy, determined randomly when they form. We observe the value we do because only universes with small dark energy can form galaxies, stars, and observers. It's an anthropic explanation that many physicists find unsatisfying, but which might be unavoidable. The multiverse idea connects to string theory, the attempt to unify quantum mechanics and gravity. String theory predicts a vast landscape of possible universes, each with different physical constants, including different values of dark energy. If universes are constantly being created with random values drawn from this landscape, then somewhere there had to be a universe like ours, with dark energy small enough for structures to form, but large enough to be detected. Some physicists have proposed that dark energy might be a kind of back reaction from the formation of structures in the universe. As matter clumps into galaxies and clusters, it creates inhomogeneities in spacetime that might average out to look like accelerated expansion. It's a controversial idea that most cosmologists reject, but it shows how desperate some scientists are to explain dark energy without invoking new physics. There's even speculation that dark energy might not be energy at all, but information. Some theories of quantum gravity suggest that space-time is emergent from more fundamental information-theoretic structures. In these theories, what we interpret as dark energy might be related to the information content, or entropy, of the universe. It's a highly speculative idea, but it shows how dark energy pushes us to question our most basic concepts. The frustrating thing about dark energy is that we have so few handles on it. It doesn't clump so we can't study it in laboratories. It doesn't interact with matter except gravitationally, so we can't manipulate it. It's the same everywhere, so we can't compare regions with more or less of it. All we can do is observe its effects on the largest scales and longest timescales, making progress painfully slow. Future observations might finally crack the dark energy puzzle. The Vera Rubin Observatory will observe billions of galaxies, mapping the expansion history with unprecedented precision. The Nancy Grace Roman Space Telescope will measure thousands of supernovae, tracking acceleration over cosmic time. The Euclid mission will map the dark universe in 3 dimensions, looking for subtle deviations from the cosmological constant. These observations might reveal that dark energy changes over time, varies across space, or interacts with matter in unexpected ways. Any deviation from the cosmological constant would be revolutionary, pointing toward new physics beyond our current theories. Even confirming that dark energy is exactly constant would be profound, forcing us to explain why this one number is so precisely tuned. Dark energy also raises philosophical questions about the nature of nothing. If empty space has energy, is it really empty? If the vacuum is a seething quantum field with real physical effects, what does nothingness even mean? These aren't just semantic questions, they touch on the fundamental nature of reality. The mystery of dark energy reminds us how much we don't know. We've discovered that most of the universe's energy is in a form we don't understand, causing an acceleration we didn't expect, with a value we can't explain. It's humbling and exciting in equal measure. Dark energy is the biggest puzzle in physics today, and solving it might require revolutionary changes to our understanding of space, time, energy, and the cosmos itself. If you wanted to write a recipe for the universe, listing all its ingredients and their proportions, the result would be surprising and humbling. The cosmic recipe, painstakingly determined through decades of observations, reveals that everything we're familiar with is just a minor ingredient in a universe dominated by darkness. Here's the breakdown. Dark energy makes up about 68% of the universe. Dark matter accounts for about 27%. Ordinary matter, everything made of atoms, is just under 5%. But even that 5% is misleading. Most ordinary matter is in the form of hydrogen and helium gas floating between galaxies. Stars make up only about 0.5% of the universe. Planets, including Earth, are a negligible fraction. The heavy elements that make life possible, carbon, oxygen, nitrogen, are cosmic trace elements, far less than 1%. This cosmic recipe wasn't determined all at once. It emerged from multiple independent measurements, each probing different aspects of the universe. The beautiful thing is that all these different methods converge on the same answer, giving us confidence that we understand the universe's composition, even if we don't understand its dominant components. The cosmic microwave background provides one of our best measurements. This ancient light, released when the universe was only 380,000 years old, carries imprints of the universe's composition. The size of hot and cold spots in the CMB depends on how much ordinary matter, dark matter, and dark energy the universe contains. By measuring these spots precisely, satellites like WMAP and Planck have determined the cosmic recipe to extraordinary accuracy. The pattern of galaxies in the universe provides another measurement. The way galaxies cluster depends on the balance between matter's gravitational attraction and dark energy's repulsion. Large galaxy surveys, mapping millions of galaxies across billions of light years, can measure this clustering and infer the amounts of matter and dark energy. The results match the CMB measurements beautifully. Supernovae give us a third independent measurement. The brightness and redshift of distant supernovae tell us how fast the universe has been expanding over time, which depends on the changing balance between matter and dark energy. Again, the results confirm the cosmic recipe derived from other methods. Even the abundances of light elements provide a check. The amount of hydrogen, helium, and lithium created in the Big Bang depends sensitively on the density of ordinary matter. By measuring these primordial abundances in the oldest stars and most pristine gas clouds, astronomers can determine how much ordinary matter the universe contains. Once again, the answer is consistent, about 5%. The convergence of these independent measurements is remarkable. It's like determining the ingredients of a cake by measuring its height, weight, taste, and texture, and getting the same recipe each time. This consistency gives us confidence that we truly understand the universe's composition, even if we don't understand the nature of its main ingredients. The cosmic recipe has changed over time. In the very early universe, radiation dominated, contributing more energy than matter or dark energy. As the universe expanded and cooled, radiation's energy density dropped faster than matter's, and the universe became matter-dominated about 50,000 years after the Big Bang. For billions of years, matter ruled, its gravity slowing the expansion and pulling material into the structures we see today. But as the universe expanded, matter's density decreased while dark energies stayed constant. About 5 billion years ago, when the universe was about 9 billion years old, dark energy overtook matter to become the dominant component. We've been in the dark energy era ever since, with acceleration replacing deceleration, expansion winning over gravity. We happen to live at a special time when we can see this transition. If we lived much earlier, dark energy would be too weak to detect. If we lived much later, all evidence of other galaxies would have disappeared beyond the cosmic horizon. We exist in a narrow window where we can discover both dark matter and dark energy, understand the universe's past, and predict its future. The cosmic recipe also varies by location. In galaxies, dark matter dominates over dark energy by a huge factor. In galaxy clusters, the densest structures in the universe, ordinary matter in the form of hot gas can be almost as abundant as dark matter, though both are still dwarfed by dark energy when you consider the full volume. In the vast voids between clusters, dark energy reigns almost unopposed, with matter of any kind being vanishingly rare. This variation teaches us something important about each component. Dark matter clumps, creating the scaffolding for cosmic structure. Ordinary matter clumps even more, cooling and condensing into stars and planets. But dark energy is utterly smooth, the same density everywhere, unaffected by the presence or absence of matter. It's this difference in behavior that allows us to distinguish these components, even though we can't see most of them directly. The smallness of ordinary matter's contribution is both humbling and puzzling. Why should the universe be made mostly of stuff we can't see or touch? Why should atoms, the building blocks of chemistry and biology, be such a minor component? There's no obvious reason why the universe couldn't have been made entirely of ordinary matter, or entirely of dark matter, or have no dark energy at all. The particular mixture we observe seems arbitrary, even unlikely. Some physicists see deep significance in these proportions. The fact that dark matter is about 5 times more abundant than ordinary matter might reflect some fundamental symmetry or relationship between these components. The fact that dark energy is becoming dominant just as intelligent life evolves might not be coincidence but necessity. Perhaps observers can only exist in this narrow epoch. The cosmic recipe also constrains what's possible in the universe. With only 5% ordinary matter, there's a limit to how many stars, planets, and living beings the universe can contain. Most of the universe's volume will always be empty space, dominated by dark energy. Most of its mass will always be invisible dark matter. We exist in the thin film of ordinary matter painted on a dark canvas. Understanding the cosmic recipe has practical implications for astronomy. When astronomers observe a galaxy cluster, they know that what they see in telescopes is just the tip of the iceberg. The visible galaxies are embedded in a much larger dark matter halo. The hot gas between galaxies, visible in X-rays, is more massive than all the stars, but still less than the dark matter. And pervading everything is dark energy, invisible and untouchable, but determining the cluster's ultimate fate. The recipe also guides searches for new physics. Any theory that attempts to explain dark matter or dark energy must account for their observed abundances. A dark matter candidate that would be produced in the wrong amount in the early universe is ruled out. A dark energy theory that can't explain its current density is incomplete. The cosmic recipe is a boundary condition that all theories must satisfy. Measuring the cosmic recipe more precisely is a major goal of modern cosmology. Current uncertainties are at the level of about 1% for each component, but astronomers want to do better. Even tiny deviations from the expected values could point to new physics. If dark energy is exactly 70% instead of 68%, that might indicate it's not a cosmological constant. If dark matter is slightly less abundant than thought, it might suggest some dark matter has decayed over cosmic time. Future missions will measure the cosmic recipe with unprecedented precision. The Euclid telescope will map billions of galaxies, determining the matter and dark energy content to a fraction of a percent. The Simons Observatory will measure the cosmic microwave background with exquisite detail, constraining the recipe when the universe was young. The Legacy Survey of Space and Time will track how the recipe changes over cosmic time. These measurements might reveal that our current recipe is incomplete. Perhaps there's a fourth component we haven't discovered yet: dark radiation, sterile neutrinos, or something even stranger. Perhaps the proportions vary slightly across the universe, indicating new physics on the largest scales. Perhaps the recipe is changing in unexpected ways, hinting at interactions between components we thought were separate. The cosmic recipe also raises profound questions about the future. As dark energy continues to dominate, will new physics emerge? Could dark energy decay into other forms of energy? Could dark matter begin to interact with ordinary matter in new ways? The current recipe might not be the final one, There's something poetic about the cosmic recipe. We're made of the rarest ingredients in the universe, the heavy elements forged in stars. We exist in the brief epoch when all components are detectable. We've developed the intelligence to discover our cosmic context, to realize we're a tiny part of a vast, dark cosmos. The recipe tells us we're special, not because we're central or dominant, but because we're aware. The cosmic recipe is also a reminder of how much we've learned and how much remains mysterious. A century ago, we didn't know there were galaxies beyond our own. Now we know the precise proportions of invisible components that dominate the universe. We can quote the cosmic recipe to 2 decimal places even though we don't understand what most of it is. It's like knowing the exact proportions of ingredients in an alien cuisine without recognizing any of the foods. Science progresses not just by confirming theories, but by constantly questioning them. The standard model of cosmology, with its dark matter and dark energy, explains a vast array of observations beautifully. But what if we're interpreting the evidence incorrectly? What if the universe is telling us something different from what we think we're hearing? These questions have spawned alternative theories that challenge our cosmic paradigm. The most developed alternative to dark matter is modified Newtonian dynamics, or MUND. Proposed by physicist Mordechai Milgram in 1983, MUND suggests that gravity itself behaves differently at very low accelerations, like those at the edges of galaxies. Instead of invoking invisible matter, MUND modifies the law of gravity to explain galactic rotation curves. In MUND, there's a critical acceleration scale, about 10^10 meters per second squared, below which gravity transitions from its familiar Newtonian form to something different. At high accelerations, like near stars or in the inner parts of galaxies, gravity behaves normally. But at low accelerations, like in the outer regions of galaxies, the gravitational force becomes stronger than Newton would predict, eliminating the need for dark matter. MUND's successes are impressive. It explains galaxy rotation curves beautifully, often fitting the data better than dark matter models. It predicts a relationship between a galaxy's mass and rotation speed, called the Tully-Fisher relation, that matches observations perfectly. It even explains some puzzling features of dwarf galaxies that challenge dark matter theories. But MUND has serious problems. It struggles to explain galaxy clusters, where even modified gravity can't account for all the missing mass. It can't easily explain gravitational lensing by galaxies and clusters. Most critically, it fails to explain the cosmic microwave background, whose patterns clearly show the gravitational influence of invisible matter in the early universe. Supporters of MUND argue these failures might be addressed by a more complete theory. Several relativistic versions of MUND have been proposed, attempting to extend the idea from Newtonian gravity to Einstein's general relativity. These theories, with names like TVES, tensor vector scalar gravity, and AQUAL, a quadratic Lagrangian, can explain some observations MUND can't, but they introduce their own complications and often seem contrived. The debate between a MUND and dark matter illustrates a fundamental tension in physics. Is it better to modify our laws of physics or to propose new invisible components of the universe? Both approaches seem radical. Dark matter requires that 85% of all matter is invisible. MUND requires that our most successful theory of gravity is wrong. Neither option is comfortable. Another alternative approach suggests that what we interpret as dark matter might be ordinary matter in forms we haven't considered. Primordial black holes, formed in the early universe rather than from dying stars, could provide some or all of the dark matter. These black holes could range from microscopic to stellar masses, and if they're numerous enough, they could explain dark matter observations. The primordial black hole hypothesis has gained renewed interest with the detection of gravitational waves from merging black holes. Some of these black holes are more massive than expected from stellar evolution, suggesting they might be primordial. If the universe is filled with such black holes, they could be the dark matter we've been searching for. But primordial black holes face observational constraints. If they're too light, they would have evaporated through Hawking radiation. If they're too heavy or numerous, we would see their gravitational lensing effects more often. There are only narrow ranges of mass where primordial black holes could constitute all of dark matter without violating observations. They might contribute to dark matter, but they're unlikely to be the whole story. Some theorists propose that dark matter might not be perfectly dark. Perhaps it has tiny electromagnetic interactions, too weak to detect directly, but enough to affect cosmic evolution. This dark electromagnetism could allow dark matter to form its own structures, dark stars, dark planets, even dark chemistry. We would be living alongside a shadow universe, invisible but complex. Other alternatives invoke extra dimensions. In these theories, gravity can leak into dimensions we can't perceive, while other forces remain confined to our three-dimensional space. This leakage would make gravity appear weaker than it should be, mimicking the effect of dark matter. Some versions predict that gravity should deviate from Newton's law at certain scales, potentially detectable with precise experiments. For dark energy, the alternatives are even more radical. Some scientists propose that cosmic acceleration is an illusion caused by our location in the universe. If we live in a vast cosmic void, a region with below-average density, the universe might appear to be accelerating when viewed from inside. It's like being in a valley and thinking the whole world slopes upward because that's all you can see from your vantage point. This void model can reproduce some dark energy observations, but it requires us to be in a very special location, the center of a void billions of light years across. This violates the Copernican principle, the idea that we don't occupy a special place in the universe. It also struggles to explain the detailed patterns in the cosmic microwave background and galaxy distribution. Another alternative suggests that cosmic acceleration is caused by the back reaction of cosmic structures. As matter clumps into galaxies and clusters, it creates inhomogeneities in spacetime. When averaged over large scales, these inhomogeneities might produce an effect that looks like acceleration. It's a subtle idea that's difficult to calculate, and most attempts suggest the effect is too small to explain observations. Some theorists propose that what we call dark energy is actually a modification of gravity on cosmic scales. Just as general relativity modified Newtonian gravity for strong fields and high speeds, perhaps another modification is needed for weak fields and large distances. These theories, collectively called modified gravity or FR gravity, can produce cosmic acceleration without dark energy. The challenge for modified gravity theories is that they must reproduce all the successes of general relativity while adding cosmic acceleration. They must explain the solar system, where we've tested gravity precisely. They must explain gravitational waves, black holes, and neutron stars. They must explain the early universe and cosmic microwave background. Meeting all these constraints simultaneously is extraordinarily difficult. There are even more exotic proposals. Maybe the universe's acceleration is caused by quantum effects we don't understand. Maybe spacetime itself is emergent from some deeper theory, and acceleration is a symptom of this emergence. Maybe we're seeing the influence of parallel universes in the multiverse. These ideas are highly speculative, but they show the lengths to which scientists will go to explain dark energy. The existence of alternative theories is healthy for science. They force us to examine our assumptions, test our theories more carefully, and consider possibilities we might otherwise ignore. Even if these alternatives ultimately fail, they strengthen our confidence in the standard model by surviving challenges. Testing alternatives requires diverse observations. We need to measure gravity in different regimes, strong and weak fields, small and large scales, early and late universe. We need to look for signatures that distinguish modified gravity from dark matter and dark energy. We need to remain open to surprises while being rigorous in our analysis. Some observations already challenge the standard model in small ways. The Hubble tension, a discrepancy between different measurements of the expansion rate, might indicate new physics. Some dwarf galaxies have less dark matter than expected. Some galaxy clusters show puzzling offsets between dark and ordinary matter. These anomalies might be errors or systematic effects, or they might be hints of something profound. The history of science suggests we should be humble about our current understanding. Newtonian gravity seemed complete until it failed to explain Mercury's orbit. The classical universe seemed deterministic until quantum mechanics revealed fundamental uncertainty. The static universe seemed eternal until Hubble discovered expansion. Dark matter and dark energy might similarly be placeholders for a deeper truth we haven't grasped yet. Perhaps the most important alternative theory is the admission that we might be completely wrong about something fundamental. Maybe we're misinterpreting the observations. Maybe our instruments have systematic biases we haven't recognized. Maybe the universe is far stranger than our current theories can accommodate. This isn't pessimism, but realism. The recognition that science is an ongoing process of discovery and revision. As we peer into the future of dark matter and dark energy research, we see a landscape of ambitious experiments, revolutionary telescopes, and theoretical breakthroughs waiting to happen. The next few decades promise to either solve these cosmic mysteries or deepen them in ways we can't yet imagine. The darkness that dominates our universe won't give up its secrets easily, but humanity has never been better equipped to chase them. The search for dark matter is entering a new phase. After decades of non-detection, scientists are expanding their search strategies, looking for dark matter in new ways and new places. The next generation of experiments will be more sensitive, more creative, and more comprehensive than anything we've built before. Deep underground, new detectors are being constructed that dwarf their predecessors. The Xenon collaboration is building a xenon T, using 8 tons of liquid xenon to search for dark matter interactions. The LUX-Zeppelin experiment will use 10 tons of xenon, making it the most sensitive dark matter detector ever built. These experiments will either find dark matter or rule out vast swaths of theoretical parameter space where WIMPs could hide. But the future of dark matter detection isn't just about bigger detectors. Scientists are developing entirely new approaches. Quantum sensors using superfluid helium might detect ultralight dark matter that conventional detectors miss. Atomic clocks could sense dark matter through tiny variations in fundamental constants. Even DNA might be used as a dark matter detector, with braking strands recording the direction of incoming particles. In space, new missions will map dark matter with unprecedented precision. The Euclid telescope, launched by the European Space Agency, will survey billions of galaxies, using gravitational lensing to create the most detailed map of dark matter ever made. The Nancy Grace Roman Space Telescope will peer deep into the universe's history, tracking how dark matter structures evolved over cosmic time. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will photograph the entire visible sky every few nights for 10 years. This massive dataset will reveal dark matter through multiple techniques: gravitational lensing, galaxy clustering, and stellar streams torn apart by invisible matter. It will be like making a movie of the dark universe, watching its invisible structures evolve. Particle accelerators are pushing into new territories where dark matter might be created. The Large Hadron Collider's high luminosity upgrade will increase collision rates by a factor of 10, improving chances of producing dark matter particles. Future colliders, like the proposed Future Circular Collider, would reach even higher energies, potentially accessing dark matter particles too heavy for current accelerators to create. The search for dark matter's identity is also broadening beyond WIMPs. Experiments are looking for axions using powerful magnets and microwave cavities. Others search for dark photons, sterile neutrinos, or even more exotic candidates. Each type of dark matter requires different detection strategies, and the future will see a proliferation of specialized experiments targeting specific possibilities. For dark energy, the future is equally ambitious. The Dark Energy Spectroscopic Instrument is creating a three-dimensional map of the universe, measuring the distances to tens of millions of galaxies. By tracking how cosmic expansion has changed over time, it will determine whether dark energy is truly constant or evolves. The Square Kilometre Array, a massive radio telescope being built in Australia and South Africa, will map hydrogen gas throughout the universe's history. This will reveal how dark energy has affected structure formation over billions of years. The telescope's enormous collecting area, literally a square kilometre, will detect incredibly faint signals from the early universe. Space missions dedicated to dark energy are in development. The European Space Agency's Euclid mission will measure shapes and distances of billions of galaxies, looking for subtle effects of dark energy on cosmic structure. NASA's Nancy Grace Roman Space Telescope will discover thousands of supernovae, tracking cosmic acceleration with extraordinary precision. Future gravitational wave detectors might reveal dark matter and dark energy in completely new ways. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging supermassive black holes across the universe. These signals carry information about the expansion of space and the distribution of dark matter. They might even reveal if dark matter or dark energy interact with gravity in unexpected ways. The future also holds theoretical breakthroughs we can't yet anticipate. Just as Einstein's general relativity emerged from thinking about the nature of space and time, new theories might emerge from contemplating dark matter and dark energy. String theory, loop quantum gravity, or some yet unknown framework might finally explain these dark components. Artificial intelligence and machine learning are becoming powerful tools in the search for darkness. AI can sift through vast astronomical datasets, finding patterns humans might miss. It can optimize experimental designs, predict where to look for dark matter, and even propose new theoretical models. The future of cosmology might be a partnership between human creativity and machine intelligence. Quantum computing might revolutionize our ability to simulate the dark universe. Current simulations of cosmic structure formation require months on supercomputers. Quantum computers could perform these calculations exponentially faster, allowing us to test theories and compare with observations in ways currently impossible. The search for dark matter and dark energy is also driving technological innovation, with applications beyond cosmology. The ultra-pure materials developed for dark matter detectors are useful for quantum computing. The massive datasets from cosmological surveys are advancing big data techniques. The precision sensors built for these experiments have applications in navigation, communication, and medicine. International collaboration is essential for future progress. Dark matter and dark energy are global mysteries requiring global efforts. The next generation of experiments involves scientists from dozens of countries, sharing resources, expertise, and data. This collaboration transcends political boundaries, uniting humanity in the quest to understand our universe. Public engagement is also part of the future. Dark matter and dark energy capture imaginations, inspiring young people to pursue science. Citizen science projects allow anyone to contribute to the search, classifying galaxies or searching for gravitational lenses. The mysteries of the dark universe belong to all of humanity, and everyone can participate in solving them. The timeline for solving these mysteries is uncertain. We might detect dark matter particles next year, or the search might continue for decades. We might discover that dark energy changes over time tomorrow, or confirm it's perfectly constant after centuries of observation. Science doesn't proceed on a schedule, and the universe reveals its secrets in its own time. There's also the possibility that these mysteries will lead us somewhere completely unexpected. History shows that big mysteries often have surprising resolutions. The ultraviolet catastrophe led to quantum mechanics. The Mercury perihelion problem led to general relativity. Dark matter and dark energy might similarly be symptoms of a coming revolution in physics. Consider what we might know in 50 years. We might have dark matter particles in laboratories, studying their properties like we study electrons today. We might understand dark energy well enough to predict the universe's fate with certainty. We might have unified quantum mechanics and gravity, explaining both dark components as natural consequences of a deeper theory. Or we might have discovered that the universe is far stranger than we imagined. Perhaps dark matter is multiple types of particles with complex interactions. Perhaps dark energy is connected to consciousness or information in ways we can't yet conceive. Perhaps our entire framework is wrong, and future scientists will look back on our dark matter and dark energy theories the way we look back on luminiferous ether. The social implications of solving these mysteries could be profound. Understanding dark matter might lead to new technologies we can't imagine, just as understanding electromagnetism led to radio, television, and computers. Understanding dark energy might reveal new energy sources, or even ways to manipulate space-time itself. These discoveries could transform human civilization in unpredictable ways. There are also philosophical implications. If we're alone in a universe dominated by dark components we can barely detect, what does that mean for our cosmic significance? If most of reality is hidden from us, what else might we be missing? These questions touch on humanity's place in the cosmos and the nature of knowledge itself. The future of darkness research is also about preserving our ability to study the universe. Light pollution threatens ground-based astronomy. Satellite constellations interfere with observations. We must protect our dark skies and quiet radio bands to continue exploring the dark universe. The future requires not just new instruments, but also wisdom in how we use our planet and space. Education is crucial for this future. We need to train new generations of scientists who can think creatively about dark matter and dark energy. We need theorists who can propose new ideas, experimentalists who can test them, and computational scientists who can simulate them. The mysteries of darkness will likely take generations to solve, requiring sustained effort across decades. As we reach the end of our journey through the dark universe, it's worth pausing to reflect on what these mysteries mean for us. Tiny, conscious beings on a small planet orbiting an ordinary star. We've discovered that we're made of the rarest stuff in the universe, that most of reality is invisible to us, that forces we don't understand are shaping our cosmic destiny. It's humbling, certainly, but it's also profoundly beautiful. There's something magnificent about living in a universe that can still surprise us. After centuries of science, after uncovering the laws of physics and chemistry, after mapping the human genome and detecting gravitational waves, the universe can still say, "You haven't seen anything yet." Dark matter and dark energy remind us that mystery isn't something to be eliminated, but celebrated. That the unknown isn't a failure of knowledge, but an opportunity for discovery. Think about what it means that 95% of the universe is dark. It means we're explorers who've barely left shore, astronomers who've only seen the stars through clouds, readers who've only glimpsed the first letters of a cosmic novel. The universe we thought we knew, the one made of atoms and light, is just a preface to a much longer, stranger, more wonderful story. This darkness isn't empty or void. It's full of structure and dynamics we're only beginning to perceive. Dark matter creates the cosmic web, the largest structure in the universe. Dark energy drives cosmic acceleration, determining the fate of everything. These dark components aren't absences, but presences, not voids, but the very foundations of cosmic architecture. The search for understanding darkness has brought out the best in humanity. It's required international cooperation, with scientists from different cultures working together toward common goals. It's pushed technology to extraordinary limits, creating instruments of almost impossible sensitivity. It's inspired young people to pursue science, to join the quest to understand our universe. These mysteries also teach us patience. Science doesn't always provide quick answers. Dark matter has eluded us for 90 years. Dark energy has puzzled us for 25. Yet scientists continue the search, knowing that understanding might come tomorrow or might take generations. This patience, this willingness to work on problems we might not live to see solved, is one of humanity's most noble qualities. The dark universe also teaches us humility. We're not the centre of the universe, not even made of its primary components. We're a tiny fraction of a tiny fraction, a cosmic afterthought in a universe dominated by invisible matter and energy. Yet somehow, through this cosmic accident of consciousness, we've developed the ability to discover our own cosmic insignificance. There's a beautiful paradox in that we're simultaneously negligible and remarkable. Consider what our ancestors would think if they knew what we know. They looked at the night sky and saw gods, heroes, animals outlined in stars. They thought Earth was the universe's centre, that the stars were fixed on crystalline spheres, that the cosmos was made for us. Now we know we're on a tiny world in a vast universe made mostly of stuff we can't see. We've lost our cosmic centrality, but gained something far more valuable: truth. The mystery of darkness also connects us across time. When we study dark matter and dark energy, we're building on work by Fritz Zwicky, Vera Rubin, and countless others who noticed something was wrong with our cosmic picture. Future scientists will build on our work, perhaps smiling at our primitive understanding, while appreciating that we did our best with the tools we had. We're links in a chain of discovery, stretching from the past into the future. These cosmic mysteries remind us that reality is far stranger than everyday experience suggests. In our daily lives, we deal with ordinary matter, familiar forces, comprehensible scales, but the universe operates on principles that defy common sense. Matter that doesn't interact with light, energy that emerges from empty space, forces that shape billions of galaxies. These aren't just strange ideas, but the fundamental nature of reality. The dark universe also highlights the power of human reasoning. We've never touched dark matter, never directly measured dark energy, yet we know they exist through careful observation and logical deduction. We've used the light from distant galaxies to map invisible matter. We've used stellar explosions to discover cosmic acceleration. The human mind, a few pounds of ordinary matter, has discovered the dark universe through pure thought and observation. There's also beauty in the incompleteness of our understanding. If we knew everything, if all mysteries were solved, the universe would be a less interesting place. The darkness gives us purpose, direction, motivation to keep exploring. Every generation of scientists can contribute to this grand quest, adding their piece to the cosmic puzzle. The dark universe teaches us about different ways of existing. Dark matter exists alongside us, passing through us right now, yet we're mutually invisible. It's like discovering we share our house with ghosts, except the ghosts are more substantial than we are. This parallel existence, this cosmic companionship with the invisible, expands our concept of what existence means. Dark energy teaches us about the power of nothingness. Empty space, which we thought was nothing, turns out to have energy, pressure, and the ability to shape the universe's destiny. It's a profound reminder that absence can be as important as presence, that what we don't see can be as significant as what we do. These mysteries also unite us with the cosmos in unexpected ways. The dark matter passing through your body right now has travelled across the universe. It was there at the Big Bang, helped form the first galaxies, and will outlast the stars. You are not separate from the dark universe, but immersed in it, connected to cosmic history and future through invisible threads. As we drift towards sleep, contemplating these cosmic mysteries, remember that darkness isn't something to fear, but something to wonder at. The dark universe isn't empty, but full of potential discoveries. Every question we answer reveals new questions. Every discovery opens new mysteries. This isn't frustrating, but exhilarating. It means the universe will never stop surprising us. The story of dark matter and dark energy is far from over. New chapters are being written right now, in laboratories, observatories, and theorists' notebooks around the world. Someday, perhaps soon, someone will make the crucial observation or have the key insight that unlocks these mysteries. When that happens, it will transform our understanding of everything, from the smallest particles to the largest structures, from the beginning of time to the end of the universe. But even when we solve these mysteries, new ones will emerge. The universe is generous with its secrets, always keeping some in reserve. There will always be darkness to explore, always be mysteries to pursue, always be reasons to look up at the night sky in wonder. So as you close your eyes tonight, remember that you're surrounded by cosmic mysteries. Dark matter is passing through you. Dark energy fills the space around you. You're part of a universe that's 95% unknown, and that's not a cause for concern, but for excitement. You live in a cosmos full of surprises, where most of reality is yet to be discovered. Sweet dreams, and thank you for joining me on this journey through the darkness that illuminates everything. Don't forget to like and subscribe to Sleepy Parallax for more cosmic journeys into the mysteries of space. Until next time, may your dreams be filled with dark matter and your thoughts with the wonder of our beautifully mysterious universe.